So, hello everybody. Before we start with statistics, again the announcement that tomorrow Mr. Geller from the Bundesbank will be here and he's talking about monetary policy in turbulent times. I think this will be quite interesting. So you are welcome to join just before later on it is the task of your fellow students to talk a little bit about prices. So would be nice if I will see some students within the room. Okay, but then we want to come to the last topic within this lecture, and in general, it should be, yeah, in a quite easy way, I have to admit, about forecasting and decision making, and everywhere there you find, yeah, concepts from statistics. Well, this is not very surprisingly because forecasting the future is uncertain, decision making, what is the best to do, having some alternatives, and all about this is at one part later on when I will talk about decision making there, I will even distinguish between a situation which we call uncertain and between a risky situation, but the concepts are always quite similar, which we use. Then maybe what I'm now talking about when we start with forecasting, well, there we will calculate average growth rates, as always in my courses, because this is one of the simplest concept to make a forecast for the future, but maybe also exponential smoothing you have maybe heard in other courses. And yeah, but we will see then. And we will also talk a little bit about seasonally adjustment, because especially here in Germany, in the midst of Europe, we have the situation that also many economic time series more or less have to follow the weather. And this is then a general statistical effect which you have, that you have a pattern of your economic time series, but the reason is not in general an economic decision, but take for example the real estate sector. We are not building that many buildings during the winter time, and therefore you find then there maybe less revenue. Or I think we have here also tourism students, and of course during summertime there are more touristic events. So if you will maybe start a touristic company, then you will of course see some under yearly time pattern. And about this, we will also talk, and then in general about decision making. And decision making is also a general topic in business administration courses. Actually, for this course here, I mixed it a little bit up, what I'm doing in statistics and what I have learned during my studies in business administration courses, because there you have always an overlap. Yeah, so, but then let's start with forecasting in general. And there is one famous statement, and you know that before I changed to economics, I did my diploma in physics. So sometimes I'm talking still about some physicists, and there's a quite famous statement of Niels Bohr, the more or less founder of the atomic model and Nobel laureate in 1922. And he said, well, prediction is very difficult, especially if it's about the future. So, and then we are here in a statistics course. And yeah, if you look up the internet, we are not quite sure if really Winston Churchill has said this or some other guy, but it is also maybe some funny statement about statistics. Don't believe any statistic that you haven't forged yourself. And well, of course, this is with a smile, but on the other hand, if you want to present something and you want in the end to sell your idea, then of course, in general, it is okay if you present your numbers and your diagrams which fit in the end your idea. But please also be careful that you do not leave anything out presenting what you want to show. So sometimes maybe it is better not to show the absolute number itself, but the growth rate. Sometimes even for your idea, it is even better to show not the first derivative, but the second derivative. So the change of the change. Maybe, but still the underlying data is the same. And in my point of view, then I say, well, then it is okay. But you are not allowed, of course, to change the data. Or in the first part of this lecture, I said the starting point is always or should be always a good descriptive analysis. But then in your personal talks and topics, then you should more talk about hypothesis testing and something like this. And then you have to be careful. This is not descriptive. Then you really have to rely on statistical data on a random sample. Within a descriptive analysis, then of course you can argue, well, here I have an outlier and because of this and that, I leave it out to focus on the mean then, because this outlier will just change your mean to everywhere where you don't want to have it. Then it's okay. But if you want to do later on then hypothesis testing, then you have to have a random sample. And if you have this number, of course, if you think of the normal distribution, it is statistically possible to have there and there also some event. And this unfortunately is then sometimes mixed up, and this to do you are not allowed. Okay, so this again as a little bit as a general statement, and then I just want to show you how in general data could look like. And then maybe this is your raw data about revenue or any quantity or something like this you find. Well, and then of course, and this is the the descriptive part, then we see almost already some pattern. So in general, we would say, well, although it is fluctuating, there is in general an increasing trend. So maybe this would be then one general explanation underlying these data. Then, of course, we this is see more or less something like a long cycle over the period of 0 to 40. Maybe this is a month, and then, well, of course, all of you maybe have heard my lecture in macroeconomics. Well, and then this is maybe a business cycle. And also, if you look at the data of your single company is working in general within the economy. And if the whole economy is following a business cycle, then it will not be very surprisingly that also your company is not one to one, but somehow also following this business cycle. Think in our times, for example, still a successful company, but of course, in general, also for every successful company, the times are quite hard right now. It would be nowadays, yeah, quite surprising if they have their best results ever during the last 30 years within these times which we have right now. So that also your revenue data or your quantities you are selling is following the general business cycle, so a longer time cyclical trend. And then we have already talked about this. Actually, we can use this example of tourism that you have, if this are months maybe, then every 4 months the weather starts, so to speak, again. And this would then maybe mean that you have an under yearly, um, not every 4 months, every 4 quarter. I think I used here quarters and 1, 2, 3, 4. Yeah. So this is then maybe quarters. And this should be also quarters. That we have a yearly trend, which we then call a seasonal fluctuation. And then something which we cannot explain, which is just a random fluctuation, a stochastic error. And I think in quite many of your topics, of your personal topics, then you have also some time series, and in the end, there is some epsilon or epsilon I. We have also talked about this when we have talked about the multiple linear regression, and there this is then assumed as a random fluctuation, maybe following a normal distribution of some volatility measured by the variance. And in general, we assume that the mean of such an error is just 0. Well, and actually, within Excel, I created so this green time series just by adding all these 4 underlying um, time series. I just added it up, and then in the end, you end up with this time series here. And now we want, to talk a little bit about possibilities if you have data like this. How could you now make a reasonable forecast knowing this historical data for the future, for the next year, or only for the next quarter, or for the next 3 years. And about this, we want to talk today. How to make a reasonable forecast. Yeah, and for this, I will present some, in this case, only descriptive possibilities to forecast. This was this other known example where you have something like in real data, you know this from the labor market that, of course, unemployment, you have a shift to the GDP data of roughly 6 to 9 months, but in general, it follows also the business cycle. And I chose unemployment data because here you have this significant seasonal pattern. Pattern plus business cycle, and in general, plus a longer term trend. Oh, this is only 22 in my macro course I showed, also up to 2015, and unfortunately we are already at 3 million. Again, so what we see then here is that in bad economic times, it is not very surprisingly that then unemployment is start to rise or starts to rise again. So this is then an example, a real data example. Maybe I find this quite fast here. Oops, and macro. Is it? There we have it. Yeah, and here you see it. This is not so nice. And the quite unfortunate thing is that we have here roughly plus 600,000 and roughly 200,000 are academics. So please be careful that you have the competences you need in the future. Yeah, so then let's go to an example. This should be our data from 2018 to 2022. We have some enterprise, and this should be revenue data in million euros, frequency quarterly, and the task is, well, we want to forecast 2023, the first quarter, or also the whole next year. And of course, later on, we will directly do this, and therefore let's open up so this one again. Okay, then question to you. What would be the most easy way to forecast the next quarter? So how will be the weather tomorrow? What would you say? Sunny, yeah. So we just look out of the window. What is the weather today? So my forecast is the weather tomorrow will be the same as today. And if you look then in a historical perspective, you won't be that bad with this forecast. So the so-called naive forecast, and this of course we use. We just choose the last data point and we say, okay, this is the next one. So the simple forecast just repeat the last data point. And actually, there is a quite broad economic field where we just assume this, that this is even the best forecast you can do. There, I hope that maybe you have heard about this already. So that you just say, this means xt plus 1 is just the expected value of today. What kind of process is just described by this dependence? Oh, sorry, other way around. I have to write it, not xt. So the expected value of xt plus 1 is just the today's value. Sorry. This describes just a random walk. And again, from physics, where we find this, this is the so-called Brownian motion. Do you remember from school where you have talked about the Brownian motion in German, Brownsche Bewegung? No. If you take just a metal stick and then I start to heat this at the one side, and then how the heat is moving through this stick. This was described by this guy in the beginning of the 20th century, Mr. Brown, and therefore we call this a Brownian motion. And then some clever guys wrote down some differential equation, the so-called Laplace differential equation, which can just describe, and if you solve this equation, then you just can directly describe how this process is going on in time. And then we say, well, there are always there some small particles within your stick, and they just start to vibrate. And the idea behind this is that the movement of such a particle is a smooth line, but at every point you do not know the derivative. Derivative is the direction of your function, and there is always no jump within it. So it is still a smooth line, but at no point you have a derivative. So at no point you do not know or you cannot directly describe the direction. So this is a smooth line without a derivative. Well, and this is then, so to speak, called a random walk. You just start to walk, and at every second you do not know in which direction you move. So, what does this have to do with economics? Yeah. Yes. Yes. So this is a very famous finding. This was done. So yeah, it started, or later on, one have found that there was a guy who modeled the development of stock market prices in the 19th century already with a random walk. And then he said, well, the stock market price itself is following a random walk, a normal distribution. But then this was fitted to the data, and then we found, well, it doesn't fit the data. So it is not a good model because a good model has to describe the history. And then in the 50s, 60s, and then the famous paper was written in the beginning of the 1970s. Then one found that not the price itself, but the logarithm of the price. And this is then more or less the growth rate of the prices. If you remember that the logarithm derivative of some function f of t, and if this f of t is now your price development during time, that this is then just the change of your function over the function itself, and this is nothing else than the growth rate of your function. And then one just took not the price itself, but you transform the price data just with the logarithm, and then you find it is quite okay. And then in the 1970s, 72, I think, Mr. Black and Scholl modeled stock, so the log of stock market prices following a random walk. So maybe then also here I write down heat equation in physics. Well, and maybe then the funny thing is they just wrote down their assumption that this is a random walk, then how the framework of the stock market is, and then they made, I think within 2 or 3 pages, some transformation of their economic model, and after this just only transforming the variables. And then after this transformation of the variables, they obtained just the heat equation of physics. And then they said, well, this is already solved 200 years ago, was solved 200 years ago. I do not have to do anything else. I just take the result, and out of this came then the option pricing model. So then option pricing model. Well, and at least when you are studying, this is then also always more or less the starting model for the capital market. I think you are talking there about a CAPM model. So this is then before that the starting point. Then you take this, and then they assumed this random walk, and out of this came then this very famous option pricing formula. So, and this is more or less still used as a benchmark if you want to sell or buy an option. That what comes out of this famous Black-Scholes model is, yeah, somehow the first starting point. Well, where should this price lie? Well, and back to our forecast. Yeah, you were totally right in the capital markets. And this then also fits, and this was another guy, they obtained the Nobel Prize, I think, in the midst of the 90s, and maybe some years before or later, then this assumption here is then a consequence of the efficient market hypothesis. So the efficient market hypothesis just stays at the stock market, at the Wall Street in Frankfurt or slash Eschborn, where the German stock market right now is situated, that there all possible relevant information is already aggregated. And out of this possible information, the outcome is the stock market price. So fully competitive, fully working, fully competitive markets. And this is the idea behind this. And if this is true, then from a theoretical point of view, again, you cannot be better than this. Well, of course, then we are in the real world, and the really good investors, they over a longer time have then the possibility, not very much, but maybe in 51 out of 100 cases, they are better than this assumption. And about Warren Buffett, it is said that he just said, well, you have to be out of 100 only in one case better than the market, and then you will be a billionaire. Yeah, okay. So, although, and therefore I talked about this, although this is a simple forecast, it has a theoretical relevance, and this should be known. Well, then, of course, we can go a little bit further in history, that we do not only use the last data point, but that we just use the last 3 data points or 4 or 5 and taking then the average out of these last period, 1, 2, 3, 4, 5, and this we call then moving average. And this means here, this is the sum of the last historical data points, and we just divide this by the number of our period. So H is then 1, 2, 3, and so on. Well, and then for practical reasons, quite often we use only odd numbers for moving average. Well, the idea behind this is then you have always a midpoint. Because of midpoint. Okay, then let's do just some calculations. 1, 2, so the simple one, 3, 5, and 7 in order to forecast the first quarter of the year 2023. Done. Oops, where's the data? Here we have it. Oh, no. And now then it is easier to manipulate the data. I just put it down here. So then moving average. And this is then H equals 1, 3, 5, and 7 we should do. 3, no 1, sorry. 5 and 7. Okay, oops, yeah, this, and we should directly save. I will also then upload this Excel file for the guys who will talk about this topic. Then you maybe can also use this for your exercises. This is forecast and decision making. So, and well, of course, we can now directly calculate the forecast using just the last 3 data points, 5 data points, and so on. But the second one is also interesting, that we, so to speak, also forecast the known historical data using the older data from before. Yeah. And then if we then plot the data with the actual data, then you see more or less also, then you see from a descriptive point of view, yeah, how fits my forecast the already known data. So then for H1 means just we are moving only 1/4 in time. This is of course the simple one. This means then we shift this just to here, and this would be Q1. And since it is a forecast, let's highlight this. Well, then with H3, we should use the last, the average of the last 3 data points, and we should move into the middle. How did I define this? That the forecasted value is then, if we put in here, for example, 3 minus 1 divided by 2. This is of course also 1. And then, since we want to center this, that we then just assume, or that we just want to forecast the data point before our last chosen one as the first forecasted data point. So, and this would be, then let's write this also down here, 1/3 times, let's then start, then we have an I is 1, so we can two, 3, 3 minus 1. In order to start with 0, I have to start with YT3. So Y3 plus, of course, no, I start with, of course, no, now I have it, sorry. So Y, this is, this is of course 1. This means now Y3, or 3 minus 1, Y hat 2 is the mean of the first 3 values. So this is then the mean of these three values, and this is now moving in time onward. So this would be our, from our data, forecasted value for the next period, and then we move on, and this is then the smoothed time series and the forecast down here. But if we center this, then of course I do not get the next point because there I have no data point. A forecast with a moving average of the last three would just the medium term, the medium point, the average of the last three data points. So this is of these three. Then for 5, we have to move one forward. Then we are using more data, but the trade-off is that we cannot smooth our data just as far as before, because still we need now for the centered values the 5 data points. So this is then from the 5, but then of course we can go only on until this. If we click on this, then you see this are then is the average of the last 5 data points. And here, this would be a forecast using this and H7, the last one, up, is the average of 7, 4, 5, 6, 7. So what is he saying here? Oop. Ah, no, it's no problem. It's only a hint that he assumes that you have done something wrong, but it is nothing wrong. But it is always also helpful if you have this green triangle here, that you have a look at it, because maybe you misspelled then something in your formula. So, and the forecast would be the mean of the last 7 data points. 1, 2, 3, 4, 5, 6, 7. And we should show our data. The first one is this one. Let's do this in black. And this should be revenue in million. To be careful. This is of course time, and that we in order maybe see a little bit more. Let's reformat this and then starting from 300 to 550. This one. 550. And let's use also this as the forecasts. Hmm. Ah, yeah, and this is actually quite often done as a descriptive way to do a forecast, and also that you have not, and you see here the black up, real data. So the black line has the largest fluctuation, and this is smoothed is smoothed via an increase of the averaging period. Of course, by one, it's not smoothed because it's only shifted by 1/4 just in a minute. And the other ones, then you see it comes down. And remember the starting point of the lecture today. Well, maybe you have something like this you cannot explain. You want just to get rid of this random part of your series in order to make a reasonable forecast for the future. So this is then, yeah, more for something like a scenario analysis, because of course you know there can be in the future also a random event, but you want to have a general feeling where is my company moving, and then you do not want, because a random fact you cannot forecast, and therefore you want to get rid somehow to get rid out of these random effects. And this one method is then this um, smoothing via moving averages. Question? Hmm. Okay, did I something wrong? Too long? No? Oh yeah, yeah. Thank you very much. Yes, this is definitely wrong. Great. So this has to be B. Thank you. And the other ones are okay. This is B, this is B, this is B, and this is also B. Great. Well, and of course, which kind you or which number you then choose, this is then your task. What are there then reasonable things where you can argue, well, I'm using a 3 or a 5 or a 7? And this is unfortunately quite similar to this choosing what what is a reasonable alpha, the error in the hypothesis testing. And because unfortunately sometimes we just said, well, alpha is always 5%, and there we have to admit this is just a number. And if it's a reasonable number for you, this you have to argue. And so also to choose which length of the period, this is then also up to you what is reasonable for you. Okay, so in general, we have a smoothing, so the fluctuation comes down using a moving average. But of course, since with an increase of the length of my averaging period, and if I have an increasing trend overall in my time series, that then I will, the longer the averaging period is, the more I in general will underestimate my data with this method. And on the other hand, of course, I will overestimating if I have a decreasing trend. Well, and of course, if I have some seasonal time pattern, so if we look at the data, oops, where is it? Then Q4, then you see here already that I just created data where Q4 is always a little bit less than Q3. Then we see here that we have within this data a seasonal pattern, and of course only using the moving average, this we ignore with this method. But we will come to this later. Yeah, and in general, yeah, it is a quite often used method to get a first idea where could be some economic data within my company in the future. And in general, it is quite often used for just making short-term forecasts. Not to say where is my company within the next 3-4 years or something like this, but just to plan. Maybe you need transportation within your company, and then just to plan how much cars I need the next month, then quite often this method of moving averages is used in order to plan, yeah, how much transportation, for example, I need in the future, in the next month. Okay, then there is another method, and this is called exponential smoothing. And why it is called exponential smoothing, this will be then next week explained by your fellow students. Um, yeah, we are now using something similar as the moving average, but now, in general, one can assume that maybe the direct historical data points, that they have a higher importance for the forecast than data points from far in the history. And in order to fit this in our forecast method, then we are not calculating just the average divided by the number, but we choose a weighted average. So this is the weighted average. And of course, here we see this is a forecasted value like we have done it just in the example before, where we have used to smooth the data our forecast method. So we manipulated historical data. If we go back here, so this 372 is a historical forecast for our known value of 366. So now we are not, as I did it wrong, as you have mentioned, do not use for the averaging process already the forecasted numbers. This we are doing now, and because this is a historic forecasted value, we need a starting point, and very surprisingly, we use as a starting point just that our first forecasted value is the value itself. So, and then we can rearrange this formula a little bit. So we just multiply with this bracket. Then we have alpha times our data point. And here we have alpha times our forecasted data point. And then we just put this in the other way together. And what we have here, then this is our historical forecasted value. And this is then somehow the error which we are doing with our forecasted value. So this is the actual data point, and this is then just the difference. So this would then mean that for the next data point, we take, so to speak, the naive forecast, the simple forecast, so the former value, but we correct this with the error of the former period. And how much we rely on this error, this depends, of course, which number we are choosing for this alpha. This is, so to speak, then the weighting of our error which we want to put into our forecast. Yeah, maybe you see then also that this is a so-called convex mixture of two numbers. And this maybe you remember from microeconomics, where you have talked about utility and indifference curves, and then you argued that this is convex, because if you take two baskets here and you draw the linear line between these two baskets, then you know, or by assumption of your utility, you are assuming that this linear line is in the better set with respect to the indifference curve. And this is just the convex. If this is basket A and this is basket B, and every point on this linear line is the convex mixture of A and B. I don't know. Have you talked about this in microeconomics? Maybe. Well, and then of course, if our alpha is in the neighborhood of 1, then of course you are more or less doing only the simple forecast, and then of course you do not have a large smoothing of your time series. And on the other hand, with a low alpha, this means you have a strong smoothing and a high relevance of older data points. And again, you know your company best. What would be a good choice of alpha? This is then again the task up to you. Okay, then what shall we do? We shall do the same thing now with alpha equals 3 and alpha equals 0.8. Oh, I have talked a lot today. Um, then let's take our data. This was moving average. Exponential smoothing. So this would be then alpha. What shall we use? 0.3 and 0.8. 0.3 and 0.8. Well, then let's go just into the formula. We are starting with the first data point, the point itself. So 300 and the second one should be then alpha. This is 0.3 and 0.8. Alpha fixing times now the actual data point, this 330 here do you have, typing the formulas, you have to be careful. Oops, sorry. Plus 1 minus, sorry, no, it works, yeah. Minus, again, alpha, this we are fixing. And now also 330, but the forecasted 330, yeah? Because if you type it like this, then I can just copy it down. So then you see here you have the first step, and then you see you are moving down to the next data point, 345, and using the old forecasted value, and of course then also the second value have also to be the same number, since 30% of 330 plus 70% of 330 is of course again 330. Yep. So, and then let's go down, and this will be then our forecast. Let's use this, and also in red. Yeah, now I can copy this formula here and only from C to D. And again, let's now have a look. Oops. 300 to 550. And revenue in million euros. This we took in black. So what else? Well, about alpha is 0. What would be this? Question to you. If you go to the formula, well, if you look at this, if this would be 0, then you have here the 0, and we are starting then here with 1, and since we are starting here with a starting point, then it is just the shift again of 1 period. And what else did I wanted from you? This was revenues per year. Well, what we see here also is that with the 0.8 in the neighborhood of 1, then we are still following more or less the old or the original data. You have not that much smoothing by if you have a small alpha, then you go in the other direction. And we want to have the yearly data 2018, this plus 1 in order to forecast. And if we are doing the same then, because if we plot the data, we already see that we have here something like a seasonal trend. And one possibility is just to aggregate over this seasonal period. And therefore, let's just, sum this up. And after this, we will make a break. So this is then the sum of 4. Unfortunately, I cannot directly copy this. 1, 2, 3, 4. And this will be the next one. 1, 2, 3, 4. Oops. Is it okay? Or did I do something wrong? No, it's still okay. 1, 2, 3, 4. And 1, 2, 3, 4. This should be the last one. Yep. Well, for myself, I also wrote a little Excel file to change quarterly or monthly and quarterly and in yearly data, because I unfortunately didn't find a good Excel add-in which is doing this. But this I have not here on at this PC. So that then we can again copy all this here, and this should almost work. Let's see. No, this does not work. This should work. And this is okay. These are the same numbers, but anyway, I change maybe this. Oh, again, I did something wrong, huh? This is not true. Oh, D and D. No, it's okay. So I can put here and down here, and then I get again my forecast. Yearly revenue again in million euros. And then let's start at 1,000 to 2,000. Do we have more than 2,000? No. Okay, yeah, these are two quite easy descriptive possibilities to do it. And what you have seen here, what I have also done is, yeah, if you have just a data set, then just start to manipulate with these different methods. And then, although maybe your manager has already said, well, choose alpha is 0.3. Well, anyway, just try it with zero point 0.7 or zero point 0.5, and maybe then you find something interesting that you can then go to him. Well, in history, you have always chosen alpha is zero point 0.3, but just see here. Now with another alpha, it fits even better. The new time series due to new numbers in the last 2 years or something like this. So what I want to say is there is no right thing you can do which is always the same. Just start to play around with data. Okay, then let's have a break.